Hello, the topic of this video is wave variables, and the essential question that you should write down in your notes is what new variables and units for those variables will we use to describe waves? So the first new variable is one that you're certainly familiar with. We used it in the last unit when we talked about kinetic motion energy, but now we're going to actually be a little bit more formal about that variable so that we can use it in an equation, and that is velocity. So the definition of velocity is how many meters something moves every second. So for a wave, it would be like when you watch that wave pulse move across the medium and you measure how many meters it's going in 1 second, that would be the velocity. The symbol for velocity is the lowercase v, so that will be the shortcut for writing this variable. The units that we will typically use is meters every second. You can also write that m over s. Of course, you're probably familiar with miles per hour, which works as well, but this is the one that scientists will tend to use. So one of the challenges in physics with variables is sometimes it's not always clear what the variable is when you sort of read about the problem or when you take data about a problem. So let's say you're at the ocean and you notice an ocean wave is covering 15 meters in 2 seconds. So maybe you have a surfer on that wave surfing it in. And the question is, what is the velocity of that wave? So it doesn't clearly state what the velocity is. You need to use the information in the word problem to figure out what the velocity is. Of course, we know that the velocity is meters we cover every second. So if we cover 15 meters in 2 seconds, the velocity is going to be 7.5 meters every 1 second, right? So it was 15 meters on top of 2 seconds. That simplifies down to 7.5 meters a second. So the next question that physicists would ask themselves about the velocity of a wave is, how could you make that wave go faster or slower? Fundamentally, you know, if you're making a wave, you're the wave source, right? You're the thing that can make that wave started. How could you adjust that wave so it could go faster or slower? So think about yourself in water or holding a slinky and sending a wave and then wanting to send a faster wave to catch up with that first wave. You can picture all the things you might do. In class, we do this as an example, and kids try all sorts of things. They try jiggling the slinky higher, they try going sideways, they try doing a faster jiggle, quicker, and it turns out you can't. The wave source can't change the velocity of the wave at all. No matter what that person does, the wave moves through that medium at exactly the same speed, which means waves never catch up with each other, right? If you picture the waves in an ocean, you never have a wave behind catching up the wave in the front. It doesn't matter how those waves look different. They never are going to catch each other because they're all moving at exactly the same speed. But not all waves in the universe travel at the same speed. So what factors do determine the wave's velocity if it has nothing to do with the wave source? Well, the velocity of the wave depends only on the medium that it's moving in. That means water waves always travel at the speed of water waves. Slinky wave always travels at the speed of slinky waves. Rope waves travel at their speed. Sound waves travel all at the same speed, right? There's nothing you can do to make your yell get to me faster as the wave source, because it's just going to move through air as fast as it moves through air without any way to adjust it. A little bit of an example here, you can see a wave hitting a boundary. We talked about that in the last video a little bit. And so this would be like having two different strings tied together. Those are different medium, right? There's a less dense one on the left and a more dense one on the right. And you'll see that as that wave moves through the less dense medium, it's going very fast. And then when the transmitted pulse goes into the more dense medium, it moves slower in that medium. The reflection is going to go at the same speed as the original wave was because it's in the same medium. So less dense in this case means faster and more dense means slower. But it's the same wave either case, right? The wave source didn't have any effect of it because that wave just hit the boundary. The second wave variable that we need to understand the use of is a word called frequency. Now, you've probably used frequency in your life to describe how often something occurs to you, and the same usage is true for waves. So when a wave source is repeating its wave motion over and over again, when we have those periodic waves, the frequency, the number of waves every second that occur are going to be the frequency. So it's how often the wave source is repeating its cycle. Another way to think of this is the number of waves every second. So if you just counted at one location in the medium and you count 1, 2, 3 for each wave that passes by, the number of waves that go by every second is going to be the frequency. The symbol for frequency is a lowercase f. Sometimes it's kind of a cursive f, so you should look out for that. And the units of waves are kind of funny. It's waves every second. It's how many every second. And scientists have a little shortcut for that. Instead of writing out waves every second, which would take a lot of work, one wave in 1 second is known as 1 hertz, or sometimes Hz. So there's a image down there that shows different frequencies of waves, so you can kind of see how they look, right? Imagine these waves are all in the same medium, which means they're all moving at the same speed, but the top wave is a low frequency, so the wave source was vibrating not very often, and the middle one is high, and then we've got ultra high at the bottom. But there's no relationship between the speed of the wave and frequency. There's also no relationship between the amplitude of the wave and the frequency. So I can have a really high amplitude wave or a low amplitude wave with the same frequency. They don't have any relationship with each other. Frequency will relate with other variables, which you'll see in just a minute though. Let's run one little example of a frequency problem, word problem. So that down there is a swordfish, and the fastest fish, which swordfish are about the fastest fish in the ocean, when they're swimming, they can beat their tails 300 times every minute. So the question would be, what is the frequency of the waves they produce in hertz? So remember, that's a wave every second. So each time we beat their tail, it's going to be 1 wave, and I want to know how many waves every second are produced. So frequency is the waves every second. We did 300 waves in a minute, so 300 waves every 60 seconds, and that simplifies down to 5 hertz. So we would have a 5 hertz wave coming out of that sword tail. And the last new variable that I want to go through today is known as wavelength. Wavelength is defined as the length or distance of one full wave. So we've talked about 1 cycle and what that looks like. If you measure that with a meter stick or a ruler, that would tell you the wavelength. It's the distance between one crest and the next one, or you could do the same thing with troughs or any other part of the wave. The symbol for wavelength is actually this funny upside down Y looking thing. It's a Greek letter known as lambda, and that's what we're going to be using as our shortcut for wavelength. Because we're measuring a distance for wavelength, the units are just meters. I can use a meter stick to measure it, and it's pretty straightforward. This is an image that shows how we would sort of notice wavelength in longitudinal or transverse waves, right? So for longitudinal, I'm just going to pick a portion of that wave that has repeatable properties. Like this is the highest pressure portion, and I would just use my meter stick to measure that distance, and that would be 1 wavelength. For the transverse waves, it's always going to be either crest to crest, or you could do the same thing from trough to trough, and it ends up being the same value either case, so the length of 1 full wave. As you'll discover a little bit later on, wavelength is a dependent variable that has a relationship with both the velocity and the frequency. Doesn't have a relationship with amplitude, but it does have a relationship with those other variables, so this ends up being the thing that we are often interested in or often able to measure. Here's a quick example of a wavelength problem. So if the slinky shown below is 6 meters long, what is the wavelength of the wave in it at the moment shown in the photograph? So this wave has 1, 2, 3 full cycles, so each of these chunks, right? And so we have 3 waves in a total length of 6 meters. And so if I wanted to find wavelength, I would say 3 waves, 6 meters on top, whoops, is the length of 1 wave. So it's the length of the whole thing divided by 3 waves, and you end up getting 2 meters for the wavelength. All right, that's it for the new variables. Take a few minutes, please, and revisit the essential question for this video, which is, what new variables and units do we use to describe waves? And write down that answer in your own words. Hopefully you wrote down some of the stuff I said, not just the things that you saw on the slide for this video. And I hope you'll enjoy this comic. It's one of my favorite ones from Calvin and Hobbes.